So we stopped here. Let me just go over the gist of what we have done so far. Essentially we are making a flame sheet assumption in this problem of co-flowing fuel and oxidizer at the same velocity, and so the flame sheet assumption basically is a infinite rate chemistry assumption or infinite kinetics, and that basically boils down to the mixing problem, and we adopt this notion called the mixed is burnt approach as far as this solution is concerned. So if you now solve only the mixing problem, all we need to do is to locate the stoichiometric surface in order to get the flame shape. So we just take the fuel and oxidizer species conservation equations in the Schwab-Zeldovich formulation and form the alphas corresponding to them for a one-step chemistry of nu ff plus nu oo gives p, and then of course you also manipulate the right hand side to look the same in these two equations for alpha, and then you now have the Schwab-Zeldovich coupling function beta that is formed as alpha f minus alpha o, and then you get a homogeneous linear equation for beta. And if you now unwrap this vector calculus equation in terms of or this equation in terms of vector identities in terms of cylindrical polar coordinates, and then we also have the fourth assumption that we listed, which is to neglect axial diffusion in preference to radial diffusion. Then we are left with these two terms. So these two terms basically signify the balance between axial convection and radial diffusion. So essentially the governing equation boils down to this particular balance that we have been discussing that dictates the flame shape. We will talk about pretty soon, we will talk about what is the consequence of retaining axial diffusion as well, but let's just proceed. This equation now is first order in Z and second order in R. That means it requires one boundary condition in Z and two boundary conditions in R, and moreover, since the boundary conditions that we can supply are at least to at most to one order less than the leading order. So the leading order here is second order in R. That means we can supply boundary conditions in the value of beta or its derivative, its first derivative, and the first derivative in beta signifies diffusion mass flux, because if you now go back and see, beta is alpha f minus alpha o, alphas are basically yi's with a normalization. Therefore a first derivative in beta will essentially boil down to indicating a first derivative in yi's, which essentially means diffusion mass flux in terms of the Fick's law to which we have reduced the Schwab-Zeldovich formulation. And since the Z boundary condition is only to first order, we can supply boundary conditions only in the value. We can't supply boundary conditions in the derivative. This is going to be pretty important for us to think about when we start looking at retaining axial diffusion sometime later. But at this stage we are recognizing that we need to have two boundary conditions either in the value or derivative for beta in R, two boundaries of R, which are R equal to 0 and R equal to B. R equal to 0 is the center line, R equal to B is the outer duct radius, and in both the cases it turns out, of course, this is a Neumann boundary condition required for symmetry, and this is a no mass flux penetrating the wall because the wall is a rigid wall, it's a non-porous wall, and you're not looking at any penetration of mass by diffusion there. Therefore these are the boundary conditions, and we can look at boundary conditions, the first derivative. Now if you now have these two boundaries subjected to Neumann boundary conditions, we have to make sure that the other boundary that we are looking at, which is Z equal to 0 for the Z boundary, is provided with the Dirichlet condition, and that's what is actually required. Okay, you can't provide a Neumann boundary condition, but when you now think about a axial diffusion taken into account, you will also have a second order in Z which will admit two boundary conditions up to first order in beta, but at that stage we can't give Neumann boundary conditions everywhere, then you will have a non-unique solution. Therefore we will think about the kind of boundary conditions admitted in that case next, but at this stage we can only provide Dirichlet boundary conditions for this and in beta. So need 1 BC in Z at Z equal to 0. So at Z equal to 0, which is a Dirichlet data, which should be in the form of Dirichlet data. So at Z equal to 0, we have to now say what should be the value of beta, right. So we now have to go back and look at how to form our beta. Beta is alpha f minus alpha o, right, and what we find is, if you're now looking at Z equal to 0, that is at the same plane as the lip of the inner duct, where the fuel is coming in and beginning to mix with the oxidizer from the outer duct. So, and we have to now look at how this the beta should span from 0 to B across R equal to A. So what we find is, between 0 R equals 0 and R equals A, you have only fuel at a mass fraction of Y of naught, and you don't have any oxidizer. Therefore your YO is 0, and your therefore alpha O is 0. So if alpha O is 0, you only are left with alpha F. So beta would be Y of naught divided by WF nu F, right, with a negative sign, because you have a nu I single prime is nu F, and you have a denominator nu I double prime minus nu I single prime. Nu I double prime is 0, so you have a negative sign over here. Therefore we are going to get a negative sign there. This is for 0 less than R less than A. Now if you now go back to what happens between R equal to A to R equals B, you have all oxidizer. That means you have a YO naught over here, but you have YF naught as 0, right. So if you now go back and see, your alpha O will be alpha O naught, and your alpha F would be 0, alright. So if you now plug alpha F equal to 0 and alpha O is equal to alpha O naught, and alpha O naught is nothing but YO naught divided by WO nu O with a negative sign, and then you have a negative sign here as well, right. So therefore you will get a plus YO naught divided by WO nu O. This is for R A less than or less than B. So what this really means is, you have now a jump in the value of beta at R equal to A, alright. It's discontinuous, but that's exactly what the mixing problem is all about. You have all fuel on one side, you have all oxidizer on the other side, and they are now going to begin to mix, right. So, and the mixing is essentially by diffusion, and diffusion is essentially a transport process, and like any other transport phenomena, the job of diffusion is to mix things and even out discontinuities, right. So it is okay to admit discontinuities at the boundary. So what's going to happen is, you have all fuel, all oxidizer, so the beta is discontinuous at the boundary, but as you now get into the domain, the job of this governing equation, particularly this term, is to even out or smoothen out this discontinuity, alright. So that is alright. So considering that we have these boundary conditions, the next step that we want to do is to non-dimensionalize. Non-dimensionalize this equation. Now many times as a student you feel that this is kind of a burden, like why would I want to do that, can't I just go ahead and solve this right away. The answer is, sometimes non-dimensionalization is done for elegance, so your governing equation will look very nice as if it has been to a hairdresser. The other times, most important technical reason is, from an engineering point of view, is you can now actually come up with non-dimensional parameters, and the non-dimensional parameters are essentially a group of quantities, so which are now grouped together in such a way that it's okay to vary one of them and not necessarily the other, or you can vary them in combinations so that the non-dimensional number is remaining constant and so on. So you can begin to see how the different parameters that are in the actual problem can group together in influencing the solution, and the solution that you obtain could be just obtained for one value of the parameter as a whole, non-dimensional parameter as a whole. You don't have to redo this for many different parameters which are non-dimensional, which are not non-dimensionalized. So it's pretty good here to basically say that, let's now say psi equals R divided by B. Now because you have a characteristic length scale in the R direction, you can non-dimensionalize by that. Unfortunately in this problem, since you have neglected axial diffusion, right, you neglected axial diffusion, it's a infinitely long duct, so you pretty much don't have a good length scale corresponding to the radial the axial direction. It's almost infinite, right. So what you're basically looking for is what is the diffusion length scale, because that's the process that we are basically looking at. In fact what we should be looking at is what is the competition between diffusion and convection, or how fast are we able to diffuse as we are convecting. Okay, it's kind of like a race between the two. The question is how much could I have diffused out this way while I am convecting at a particular rate. That's now going to give me a certain length scale associated with this, right. So that's going to be made by saying, if I now have my eta equals z, let's say z by u divided by b squared over d, right. So z by u is essentially a convective length scale, and b squared by d, keep in mind d has the units of like meter squared per second, right. So b squared has meters, meter squared, therefore this has a units of time, right. And so z by u also has units of time, and therefore eta becomes non-dimensional, but in this the only variable is z. Okay, so the farther you go and as you convect, you now have the more time you are taking, but in this time you are also diffusing this way. That's because b is the length scale corresponding to diffusion, because the diffusion is predominantly radial, right. So if you want to put these two together, then this is the zd divided by ub squared. As a matter of fact, you could begin to think about this as, if I were to say I don't know any of this, let's say I'm not interested in thinking about the actual problem. The professor asked me to non-dimensionalize. I see b as my parameter, the length scale here, and that fitted in fairly well with psi. Why can't I do the same thing with eta? I would like to think of this as just z by b. Then you have all the stuff sticking out, which is essentially d divided by ub. Now ub divided by d essentially is the counterpart of your Reynolds number that you would use in momentum mixing, but here this is species mixing, so you would actually have to use the Peclet mass transfer number, which is the corresponding part of this. So this is 1 over Peclet, where Pe is ub divided by d. Right. So from here we can begin to think, if Peclet is kind of small, all right, then eta becomes proportionately larger. Okay. So Peclet small is basically meaning that you have less convection relative to diffusion. Okay. So you would expect that you have more and more diffusion happening this way, but less convection happening that way. So you should actually be able to get your flame to be shorter. So that's what you should expect for smaller Peclet numbers. because you are not going too far along the convective path, rather you are diffusing. So your flame should all be confined to closer to the burner because you have diffused a lot. Therefore a smaller Peclet number will correspond to a shorter flame effectively, and we are trying to cover the shorter flame by artificially blowing up the eta, having this 1 over Peclet there essentially. So effectively this takes into account that effect. But your governing equations do not take into account axial diffusion, so that is something that you have to keep in mind. That is what should really make the flame shorter, strictly speaking, how the governing equation turns out to be. Further you can form some more non-dimensional parameters. Let C be equal to A by B, and I will make a big deal about this and the next one, which is nu equals alpha O naught divided by alpha F naught, okay, alpha O naught divided by alpha F naught. If you want to now go back and see what those are, this is nothing but alpha F naught would be YF naught divided by WI nu I with a negative sign, alpha O naught would be YF naught YO naught divided by WO nu O with a negative sign. So the negative signs cancel each other. All you are going to again be dealing with is Y O naught divided by WO nu O divided by YF naught divided by WF nu F, alright. And we will come back to this and this quite soon. We have non-dimensionalized R, we have non-dimensionalized Z, and then we have a couple of now new non-dimensional parameters in the problem, but we have not non-dimensionalized beta. Okay, so let gamma be equal to beta divided by alpha F naught. That is to say, if you now were to basically go back and say alpha, we just have to pick one of those two, right? We just pick alpha F naught. So beta divided by alpha F naught would be alpha F divided by alpha F naught minus alpha O divided by alpha O naught is what we are going to, sorry, alpha F naught, okay. So you just have a alpha F naught in the denominator just to go with this. You can also see that this goes with this. Here we have divided alpha F naught in the denominator, therefore we are using this. So the way the nu is defined is how the way gamma is also defined, okay. Now the interesting thing, if you now do all these things, the governing equation then becomes dou gamma by dou eta equals 1 over psi dou by dou psi of psi dou gamma by dou psi. So essentially we got rid of u by d completely, alright. So that is because that information is actually buried in eta. We have scaled our eta corresponding to the competition between axial convection and radial diffusion. That is what this signifies, right. So we now have a very nice looking equation without any parameters. So this solution is now going to give you this equation is now going to give you a solution without any parameters, except the boundary conditions are now going to carry some parameters. So what are they? The boundary conditions are the non-dimensional boundary conditions are so now we have to write in terms of gamma. So gamma equals let's first write the Neumann BCs for psi. That's very easy. At psi equal to 0 we have dou gamma by dou dou psi equal to 0, and at psi equals 1 we have dou gamma by dou psi equal to 0 for all eta greater than 0, right. In fact we should have gone back and said right here for all z greater than 0, that's true for the entire domain further out. Then so this is the boundary condition for psi in, so for gamma in psi, but what happens to gamma in eta, right. So and gamma, we now have to translate this boundary condition in non-dimensional form. That simply turns out to be 1. Recall we had this is basically alpha f naught, okay, and then we just form a gamma by dividing by alpha f naught. So we need to get a do we have a negative sign? With the negative sign is alpha f naught, okay. So with the negative sign is alpha f naught, and we just divide by alpha f naught, therefore you simply get a 1. And similarly, if you now go back and plug in here, this is actually minus alpha o naught, okay, with the positive sign. This is minus alpha o naught, and then for trying to find the gamma you divide by alpha f naught. So minus alpha o naught divided by alpha f naught is nothing but minus nu, okay. But where are they? We can now write this is actually 0 less than psi less than c, c less than psi less than 1. So even though your governing equation did not have any parameters, there are a couple of parameters that have crept into the problem in terms of nu and c through the boundary conditions, alright, and this is going to be very, very important. In fact this is actually only one boundary, that is at eta equal to 0, right. Basically that's the boundary that is describing the problem for you. If you did not have fuel and oxidizer initially unmixed entering the domain at eta equal to 0, you didn't have a problem, okay. So this essentially tells you that the fuel and oxidizer are in, as they enter the domain, are unmixed, and that's what the problem is. So all the parameters in the problem are now reduced to just these two, okay. So with this I'm not going to derive the solution for you, and I'm going to assume that you know how to derive this, okay. And the way to do this is you seek a product solution. That means you now say gamma is a function of gamma is now a product of two functions, one function which is a function only of psi, another function that's a function only of eta. So you now have let's say seek a product solution of the form, let us suppose gamma equal to some function chi that's only a function of psi, and another function, let's say I don't know what's a good symbol. Well, you could just go back with Anglo-Saxon variable, so you can simply say capital X of psi and capital Y of eta, alright. So if you did this, plug it back in here, go through the product solution approach and substitute these boundary conditions, noting that you are expecting to have a periodic solution in psi because you have homogeneous boundary conditions there. This is a inhomogeneous boundary condition here, so you are not expecting periodic solution in eta, and so on. You do all those things and you can now find the solution to be the solution is gamma equal to 1 plus nu c squared minus nu plus twice of 1 plus nu times c summation n equal to 1 to infinity, that means it takes integer values, 1 over phi n j1 of c phi n divided by j naught of phi n squared times j naught phi n psi e to the minus phi n squared eta. I don't even understand this, right? Well, let's just go step by step. I mean, of course we are not as intelligent as we would like ourselves to be, so all these things are something that we have seen. Okay, these are part of the parameters of the problem. The first time we encounter a problem now is what's phi n. So phi n is what is called as the nth zero of j1 of phi, where j1 is a Bessel's function, right? So that's a Bessel's function of first order. So obviously then j naught is the Bessel's function of 0th order, right? Now what is Bessel's functions? Bessel's functions are those that look like sines and cosines. In fact j naught and j1 will look like sines and cosines, except that they don't have a constant amplitude. So you will now find that they kind of keep decaying but keep alternating about the horizontal axis, right? So that's the kind of solution that you're going to get, and you now have a summation over a series of those. So phi naught phi n being the nth zero of j1 of phi essentially means that this function keeps on alternating up and down about the horizontal axis at specific values of phi, the argument, right? So when you say zeros, those are the values. So where all do you have the j is going to 0 is essentially where you get these values of phi, okay? So it's kind of like in sines and cosines. If you take a sine wave, you know that the sine wave passes 0 at 0, pi, 2 pi, 3 pi, 4 pi and so on. So those are the zeros of the sine function. So similarly we will have these. What will happen is you will find that these are not actually equally spaced, they have a certain pattern, alright. So that's how the Bessel's function behaves, and typically we get into a Bessel's function mainly because you're having this kind of a derivative for cylindrical polar coordinates, and that's mainly because we are using axisymmetric pipes, okay. So instead if you now had like vertical plates like channels, right, you will not have a complicated looking derivative for the Laplacian. You will simply have a partial squared beta divided by partial squared, or partial squared gamma divided by partial squared psi, partial psi squared, and you will get sines and cosines, and typically for these kinds of boundary conditions you should get cosine, a cosine function here, and that would actually imply that we are fitting, strictly speaking what it really means is we are fitting this particular discontinuity by a Fourier expansion and then letting the Fourier expansion decay, okay. So essentially you now have a step that is represented by a Fourier series, and then it's subjected to boundary conditions of Neumann BCs on either side, and then as you keep on mixing more and more, this particular function now changes, and essentially the Fourier representation keeps changing as you go along until you get a more and more uniform variation in the mixed diffraction. Instead of a Fourier series, you now have a series that's based on Bessel's functions, and that's possible. Anytime you are looking at functions that are orthogonal to each other, like in terms of sines and cosines you will have orthogonality, in Bessel's function also you have orthogonality. So based on these you can actually form series that look like Fourier series but not necessarily in sines and cosines but some other orthogonal basis functions. That's what we have done here. okay, or that's how it comes out to be when you now pursue the product solution. How do you know it's a product solution? Because you now see the psi dependence actually here and the eta dependence here, it's a product. Okay, so you don't have psi and eta mixing up with each other. They are separate, but they are multiplying. The functions containing them are multiplied with each other. And we also see that you have a e to the minus phi n square, sorry, e to the minus phi n squared eta. That's an exponentially decaying term in eta. So what that basically tells us is, as you now go to eta tending to infinity, farther and farther from the Bonner lip, this entire term is going to go away, and you are now going to get a gamma that is only this term. Alright, and gamma is nothing but beta normalized, and beta is nothing but a difference in normalized mass fractions, and normalized mass fractions are this. So essentially it tells you that as you go further and further out, the mass fractions are going to differ by a constant. Alright, and the constant depends on two things, nu and c. So now we have to think about what does nu and c basically mean. They mean something very interesting. Nu is telling us yo naught divided by wo nu o divided by yf naught divided by w of nu f. This has got nothing to do with the geometry of the problem. It's got to do with our inlet mass fractions of oxidizer and fuel and their respective molecular weights and their stoichiometric coefficients in the reaction, in the single step stoichiometric reaction. Okay, this is a stoichiometric reaction. That means you don't have either fuel or oxidizer left over as part of the products. So what are the stoichiometric coefficients required for them to react with each other completely, right? That's what is contained in this. So this is a mixture quantity and it's a inlet quantity because it has yf naught and yo naught. C on the other hand is purely a geometric parameter. It tells you how small or large is the inner duct relative to the outer duct. Okay, so now you have to think about many different combinations. Is it possible for me to have a very small inner duct relative to a very large outer duct, but send a high concentration of fuel inside when compared to a very diluted concentration of oxidizer outside? Let's suppose that that's one possibility. The other possibility, I now have a fairly fat inner duct and just a little bit bigger outer duct. That means most of the outer duct is contained by the inner duct, and you are essentially trying to send a lot of fuel, but let us suppose that the fuel is highly diluted but the oxidizer is highly concentrated. What kind of flames will we get? Right, on the one hand you are trying to send a very concentrated amount of fuel but in a very small region. On the other hand you are sending in a lot of fuel, alright, but it is actually highly diluted. Would you happen to have the same kind of flame? Right, so that's what this is going to dictate. Okay, so what are we going to look for in this? What we want to see is, interestingly, this is now a gamma that's a function of eta, psi and eta. That means we should be able to plot gamma in this domain in where the mixing is happening, and all we are looking for is look for gamma equal to 0, right, as the stoichiometric surface which is essentially the flame shape. So that means if you are able to plot this particular function in the domain and have a contour map of gamma, you now look for the gamma equal to 0 contour, the iso contour of gamma equal to 0, corresponding to gamma equal to 0. So what does gamma equal to 0 mean, right? Gamma equal to 0 means, or beta equal to 0, if beta is equal to 0, then your alpha f equal to alpha o. Back here, right? So gamma equal to 0 means beta equal to 0, beta equal to 0 means alpha f equal to alpha o, and alpha f is nothing but minus yf by wf nu f, which is equal to minus yo divided by wo nu o. All right. So what this basically means is we want our yf by yo along gamma equal to 0 to be in the ratio of wf nu f divided by wo nu o, right? And what does that mean? If I were to simply say nu f by nu o, that would mean the stoichiometric ratio in terms of moles, right? All I have done here is to multiply nu f by wf and multiply nu o by wo, so I am essentially looking at the mass ratio, okay? So this is the mass ratio of stoichiometric proportions of fuel and oxidizer in a reaction for complete reaction to happen. And what you are basically saying is when nu f by nu o anywhere in the domain is in this ratio, you have a stoichiometric surface, and that's what the flame is, that's what the flame sheet assumption is, that's what infinite chemistry means, that's what mixed is burnt approach is all about, right? So effectively it all translates to saying just look at the gamma equal to 0 contour. All right. Further, let's look at, go back and see what nu is in the light of what we have done, right? So this implies we can write, or we can simply write this equal to nu o divided by nu fo, right, divided by wo nu o divided by wf nu f. So what nu signifies is the incoming oxidizer fuel ratio by mass to the stoichiometric oxidizer fuel ratio by mass, right? So effectively nu tells us something about what is coming into the domain relative to the stoichiometric mixture ratio, and C tells us how much of what you are getting. All right. So what you are then saying is we can now begin to do a few things here. One, how does the height of the flame get determined, right? So how does the flame look like? What will happen if you now try to plot this contour for gamma equal to 0, right? So depending upon the values of your nu and C, right? So if you now say this is your psi equal to 1, psi equal to 0, and you now fix your C as psi equal to C, that's where the inner tube ends and then the outer tube is there. You could now get a flame that either looks like this, or in fact we have a wall there, you could have a flame that looks like that. As you now change your nu. So for different values, so if you now fix your C at a particular value and change your nu, you can get the flame to close over the fuel, or you can get the flame to open up and close over the oxidizer, open up from the middle and close over the oxidizer. All right. So this is now called the overventilated flame, and this is what is called the underventilated. Right? What does that mean? You're essentially having a concept of ventilation as in opening up more air, or so when you now say overventilated, that means you have a lot of air when compared to fuel, so the flame is actually closing over the fuel and consuming all the fuel. And if you now say underventilated, that means you don't have enough air, so the fuel is spreading out and then mixing with whatever little air it can, and then having and meeting it at stoichiometric proportions along this line that closes over the oxidizer and opens up over the fuel. So by this what it means is, if you now have a flame that looks like this, you now have a fuel rich region over here, or pretty much all fuel in the actual case, and outside is going to be oxidizer, because the flame is separating the fuel and oxidizer and getting them to meet at stoichiometric proportions in between. Alright. So if you now have a underventilated flame, you are simply going to have a lot of fuel that's going to go out unreacted over here. So when would you expect a fuel rich when would you expect a underventilated flame or a overventilated flame? So now think about those two limits that we were talking about. If you now have a very short duct for the inner duct, very small duct for the inner duct when compared to the outer duct, and you are having infinite domain, pretty much no matter how concentrated the fuel is relative to how dilute the oxidizer is, you are very likely to have a flame that is closing over the fuel. That means it's going to be an overventilated case. If you now have a very broad inner duct when compared to the outer duct being just a little bit bigger, you're very likely to have a opened up flame that is underventilated. Right? No matter how much you are diluting things, but there is an effect of that, and that effect is going to come up when you have you're at a 50-50 kind of situation. That is, you're neither too small nor too large. The message here is the slot width is going to dictate whether the flame is going to be overventilated or underventilated more than nu. Or in other words, the far field behavior of the flame is more sensitive to C rather than nu. So what is the job of nu in this? Then you have to ask yourselves, look at this picture. This flame, if you are now somewhere here, you are just beginning to look at how this mixing is happening, and then the flame is shaping up. Both of them are beginning to look pretty much the same. They are going like that over the oxidizer, starting from the fuel, right? But then as you keep going, that went that way, this went this way, and then we now call this overventilated, that one underventilated. But why did they start going like that in the first place? Right? Why couldn't you have a flame that was like this? That could have been a possible solution as well. So what is the difference between this and this? This flame started going over the fuel and closed over the fuel, whereas this flame started going over the oxidizer and then closed over the fuel. This flame goes over the fuel and closes over the fuel. So you now have multiple possibilities. You could have a flame that starts going over one of the ducts and then closes over the other, or it goes over the same duct and closes over the same duct, right? So what governs this is nu. When they are just beginning to mix and react, they are just beginning to consume the reactants, and it's the final large scale availability of reactants that's going to shape up how the flame is going to end up as we go along, and the large scale availability is dictated by the C, how much fuel you have on the whole versus how much oxidizer you have. But locally, as they just begin to mix and react, they are not worried about that. They are not worried about how they are going to end up when all the less deficient species is consumed, reactant is consumed. They are going to first be dictated by what is the new, how concentrated the oxidizer is relative to the fuel as it comes in relative to what their stoichiometric ratio demands. So if you had a fairly concentrated fuel but coming in a very, very small region, it's going to actually go out in search of the oxidizer, because oxidizer is dilute, alright, and ultimately as you go along you're having a short fuel duct, a small fuel duct, so you're running out of fuel and then it closes over. So you can see that the nu dictates the near field behavior of the flame and the C dictates, not both of them are together, it's difficult to separate them, but you look at the sensitivity, right, you look at the sensitivity of this, the far field behavior of the flame is more sensitive to C, the near field behavior of the flame is more sensitive to nu, alright. And then from this you can also find out what should be the shape of the flame. So what should be the combination of nu and C together that will give rise to a optimally ventilated flame, right, a flame that's kind of like that. But I just went too fast, I didn't tell you whether it's going like that or like this, right, that depends on the nu. What I'm talking about is for a given nu, what should be the C such that the flame goes vertical. And does it go to infinity? We'll talk about it later.